This is the 34th video supplement for CIS 351, Grand Valley State University's course on computer organization and assembly language. This video talks about jump instructions. Thus far, we've built a CPU that can execute a sequence of arithmetic and logic functions. These instructions can take as input either 2 registers or 1 register and an immediate value. The next thing we need is a means of flow control. When you execute a program, you don't usually run your source code in order right from the beginning to the end, because things like loops, function calls, and if statements change the order the code's run in. Therefore, our CPU needs instructions to support these constructs. Let's begin with jump. A jump is effectively a go-to statement. So consider this assembly code. It doesn't do much interesting on its own. It just provides some initial values to registers. But suppose for some reason you wanted to skip over the initialization of T3, T4, and T5. We could place a label, let's call it target, and then we can add a jump instruction to that label. When I step through the code line by line, you can see that when we get to the jump instruction and execute that jump instruction, control skips to the instruction marked with that target label, the instruction that assigns an initial value to T6. The task now is to add this instruction to our CPU. So, at a high level, how does the jump instruction work? What happens inside the CPU to make the desired target instruction run instead of the instruction immediately following the jump? In our specific case here, how do we make the T6 instruction run instead of the T3 instruction? So pause the video and think about that for a minute. Okay, so if you didn't quite figure it out, think about it this way. What part of the CPU determines which instruction is being executed? Well, the program counter. The key idea is that the jump instruction needs to put a new value in the program counter. All right, so what is this new value? How do we specify which instruction we're jumping to? The assembly code uses a label, but how do we encode the label in a machine instruction? Well, that was a trick question. We don't. How does the CPU identify instructions? By their address. If you look here, you can see that each instruction has a unique address. This is the address of that instruction in RAM. And then here you can see that the assembler replaced the label target with the actual address of the instruction we want to jump to. This is the instruction where we set T6, and this is the address of that instruction, and it's that value that's placed up here. Now, in theory, we could write assembly code using addresses instead of labels, but that would just be a nightmare. You would have to adjust the labels every time you added or removed lines of code. This system of using labels is much better because the assembler automatically computes the correct address for you. And if you add or remove lines of code, like I'll do right here, you just reassemble the code, and you can see that the assembler automatically recomputed the address in place of the label. That means the programmer doesn't have to worry about figuring out which labels changed, or if they did, what the new values are. So, to implement a jump, we need only take the target address out of the instruction and place it into the program counter. To do this, we add an additional data path, a MUX, and a control wire for the MUX. When the control unit sees the opcode for a jump instruction, it places a 1 on the jump control wire, which causes the new value for the program counter to come from the instruction. For non-jump instructions, the control unit places a 0 on the control wire, which causes the new value for the program counter to be the current value plus 4 as usual. One problem. An instruction address is 32 bits. But we only have 26 bits available in the instruction, 32 less the 6 bits for the opcode. So what do we do with the other 6 bits? First, notice that every instruction address is a multiple of 4. A little bit easier to see in decimal here, right? 4, 8, 12, 16, 20, 24, and so on. When I show these addresses in hexadecimal, we can see that they all end in 0, 4, 8, or C. If you write all of these numbers in binary, you'll see that they all end with 2 zeros. Now this of course isn't a coincidence. It happens for the same reason that multiples of 100 in base 10 end with 2 zeros. But since these 2 zeros appear in every jump instruction, we don't need to include them in the instruction itself. We can add them in the CPU itself by adding 2 bits to the end of the target address field in the instruction. 26 bits go in, we add 2 zeros to the end, and 28 bits come out. Now that helps, but we're still 4 bits short. We still need a 32-bit address. Now what? For this, we need to rely on convention. When you run a program, there's a variety of things that need to be stored in RAM, not just the instructions. For example, you often have more data you need to store than will fit in the registers, and that data will go in RAM. You also need to set aside some space in memory for the operating system to use. This diagram shows the conventional addresses used for these purposes in MIPS. By convention, instructions are placed in what we call the text segment. Think of your source code as text, something you can read, in contrast to the values in your variables, which are called data. This map shows that the text segment begins at address 00400000. In fact, this is what you see if you look at the text address in MARS. First instruction is at 00400000. Now from this map, you can see that the conventional place to start putting your data begins at 10000000. Thus, instructions have addresses that range from 00400000 to 0FFFFFFC. If you add 4 to this last address, then you get the 10000000 where data begins. The important thing about this range with respect to jumps is that all the instruction addresses, when written in binary, begin with 4 zeros. MIPS takes advantage of this by taking the most significant 4 bits from the current address and using them as the most significant 4 bits of the jump target as well. This works for user code because those 4 bits are always 0. So now we have the complete implementation of the jump instruction in MIPS. But before wrapping up, let's take a minute to make sure that the process of encoding a jump instruction is clear. So let's say your assembly contains the instruction jump to target, where target is a label somewhere in your code. When you assemble the code, the assembler will figure out the address of the instruction with the target label on it. Suppose in this case that address is 0040001C. We exclude the 2 bits at the end because we know there'll always be 0. Therefore, there's no need to spell that out in every jump instruction. We also exclude the most significant 4 bits because we assume that they're the same as the leading bits in the jump instruction's address and therefore are available elsewhere in the CPU. We then take the 26 remaining bits and put them in the machine instruction. Now, jump instructions are important, but they aren't terribly useful on their own. In the next video, we'll look at branch instructions. When used together with jumps, branches are what allow us to write conditionals and loops in assembly.